In this lesson, we're going to take a look at logarithmic and exponential equations, and we're going to discuss the process of solving them. Now, solving an exponential and logarithmic equation is similar to all the other types of equations we've solved, except for one thing. We've been using this analogy between logarithms and exponentials in that they communicate the same thing, just in a different language. So, the key to solving exponential and logarithmic equations is that at some point in the solving process, if you started with a logarithm, you're going to have to convert from log form to exponential form. And likewise, if you start with an exponential equation, at some point you're going to have to convert to log form. What that does is it removes the variable from the location where the equation is unsolvable. So let's take a look at this first one as our example. We have 5 times the log base 4 of x equals 15. I need to solve for x. Okay, so what I'm going to do is I'm going to do this simple stuff first that we've done for years now in solving equations. I'm going to divide the 5 away. Divide by 5. And now I've got the log base 4 of x is equal to 3. Now the log base 4 of x is one piece or one statement. Like, it's not log base 4 times x. I can't divide the log base 4 away so that I leave the x, because the x is a part of the log base 4. So it's at this point when there's nothing else to divide away or add or subtract away or multiply away. There's no exponents to deal with anywhere. It's at this point that we convert from logarithmic form to exponential form. So in doing that, it produces, we start inside, that's x equals 4 to the third is the conversion from log form to exponential form. You can see that by doing that, that x is now out of the parenthesis inside the logarithm, and now it's equal to a set of constants that I can now simplify. 4 to the third power is 64. So there's the solution to our logarithmic equation. Okay, let's see that at work again. We're going to work a couple more examples to drill that home. Here's the next example we have. We have 2 times the log base 8 of x plus 9 minus 8 is equal to 2. Okay, so first I'm going to look for the things that I can peel away. I see that I have a minus 8 that I could add to both sides to get rid of it here, and then it comes over here. So I have 2 times the log base 8 of x plus 9 is equal to 10. Now I see that I have a 2 floating around out front that I can divide away. So I'm going to divide that 2 away, and I'm going to bring it as log base 8 of x plus 9 is equal to, now 10 divided by 2 is 5. So because everything left is inside the logarithm on that left-hand side, this is the point at which we convert from exponential form, or logarithmic form, into exponential form. So that becomes my x plus 9, which is in the logarithm, equals 8 to the 5th power. Now that's going to be a fairly large number, so I'm going to get my calculator out here. I'm going to go 8 to the power of 5. So that gives us x plus 9 is equal to 32,768. I can finish this off now by subtracting 9 from both sides, and that produces x is equal to 32,759. So as you can see again, we're doing things similar to what we've done with all sorts of other types of equations, but it took a conversion from log form to exponential form to finally finish it off. Okay, we've got a couple more examples we want to look at now. Here we've got log base 2 of 3x plus 13 is equal to 17. So in looking at that problem, I first see that I've got a 13 that I could subtract away from both sides. And that produces the log base 2 of 3x is equal to 17 minus 13 is 4. Okay. Well, that was the only thing outside the logarithm that needed to be moved over to the other side. So it's at this point, again, that I now convert to exponential form. Doing that produces 3x equals 2 to the 4th power. Okay. So again, the x is put in a location where I can now finish solving for it. So that's 3x is equal to 2 to the 4th power. 2 times 2 is 4, times 2 is 8, times 2 is 16. So 3x equals 16. I can finish this off by dividing the 3 away from the x, and I end up with x is equal to 16/3. So there's the exact solution. If we wanted to, we could state this as x equals 5.33 repeating. Great. So that's to take a look at logarithmic equations. You can see that in these equations, again, we are converting from log form to exponential form as that extra step in order to be able to solve these equations for the variables. Well, now let's start with the opposite type of equation, an exponential equation. In this case, the variable that we're solving for is the exponent. Right? X is the exponent. Well, what this is going to take is us converting from exponential to logarithmic form. But like the other problems, there's some things that we want to do first. We want to peel everything away and move it from the left side to the right side as much as possible. So I'm going to start by subtracting 9 from both sides. Produces 3 times 2 to the x is equal to 30. Okay, now I'm going to divide by 3 because the 3 is attached to the 2 through multiplication. That becomes 2 to the x equals 10. Now it might be tempting to say we divide both sides by 2, but 2 is not connected to the x by multiplication. X is the exponent. So in order to get that x by itself, I don't divide by 2, I convert from exponential into logarithmic form. So that ends up looking like x equals log base 2 of 10. What I can now do is go to my calculator and figure out what is the log base 2 of 10. And it ends up being 3.32. So you can see in this first example of solving an exponential equation that we're doing the exact opposite of the other problems. There's a point at which we have to convert from exponential into logarithmic form. And in logarithmic form, we can finish solving the equation. Here's another example. I'm going to do a couple more exponential equations. As you look at this problem here, the x is on the left-hand side of the variable. We're trying to solve for that x. I'm going to first start here by adding 8 to both sides. And that produces 5 to the x plus 3 is equal to, I believe that makes 81. 73 plus 8 is 81. Now there's nothing in front of the 5 to divide by, so at this point we're already at the point at which we're going to convert into logarithmic form. That becomes my exponent of x plus 3 is equal to log base 5 of 81. Log base 5 of 81. So I can go to my calculator again and do the log of 81, comma, base of 5. Okay, and that is x plus 3 is equal to 2.73 approximately. Last thing I need to do here is subtract 3 from both sides. So that becomes x equals, subtract 3 from that exact value, it becomes x equals approximately negative 0.27. There we go. X equals negative 0.27. Okay, 2 more examples that we want to look at. These examples are unique in one specific piece that we've got going here. you can see that one of the values in our equation is e. Now I say value, not variable, because e, as you guys remember, is a number. E is a specific number having to do with continuous growth rate. Okay, so let's start this like normal. I'm going to start by subtracting 14 from both sides. It's 5 times e to the negative 3x is equal to, let's see, 89, it's a 79, I believe. 93 minus 14 is 79. And then I'm going to divide, that 5 away, because it's 5 times e to the negative 3x. So I can divide that 5 away. And that produces e to the negative 3x is equal to, let's see, 5 goes into 75 15 times. So that's going to be 15 and 4/5, which is 15.8. So 79 over 5 is the 15.8. Okay. Now everything is peeled away from that exponential piece, the e to the negative 3x. So it's at this point that I convert into log form. That produces negative 3x is equal to log base e of 15.8. Now you notice the unique thing here is that we ended with a log base e. If we recall, we'll remember that log base e is natural log. So it can be rewritten as negative 3x equals the natural log of 15.8. Now I can go ahead and do that in my calculator with the natural log button. Natural log of 15.8 produces negative 3x equaling 2.76. I can finish this off by dividing by negative 3. And that produces x equaling negative 0.92. Negative 0.92. Great. Let's do that one more time just to solidify that idea of using e. So here's another equation that we've got here. 15 minus 4 times e to the x minus 9 is equal to negative 32. We'll first start by subtracting 15 from both sides. Okay. So that produces negative 4e to the x minus 9 is equal to, subtract 15 from that, that's 30, 40, so negative 47. Negative 47. Okay. But now I've got this negative 4 that's being multiplied by, that's multiplying the e. So I'm going to divide that negative 4 away. That's e to the 7 minus 9 is equal to, let's see, 4 goes into 40 10 times. 44 11 times, so that's going to be 11 and 3 out of 4 left over, so 11.75. And the negative over a negative makes it a positive. So again, negative 47 divided by negative 4 produces that 11.75. Now that it's in simplest exponential form possible, I'm going to convert into log form. It becomes x minus 9 equals log base e of 11.75. Again, that log base e, we know anytime the base value of a logarithm is e, that it is a natural logarithm. So that's x minus 9 is equal to the natural log of 11.75. So a natural log of 11.75. Do that, that's x minus 9 is equal to 2.46. To finish that off, I'm going to add 9 to both sides, and that produces x equals 11.46. So there's several examples of how to solve both logarithmic and exponential equations. Again, that key is that at some point either way you're going to have to convert from log form to exponential form or exponential to log form.